Hello, my name is Amashni. In our previous lesson, we examined the geometrical property of similarity. In today's lesson, we will investigate more closely the relationship that we found about the size and angles of similar triangles. By the end of this lesson, you should be able to describe the angle-angle rule of similarity, describe the side-side-side rule of similarity, describe the side-angle-side rule of similarity, and use your knowledge of similarity in problem solving. To start this lesson, we are going to make a conjecture. Remember, we used a conjecture to solve a problem in lesson 1. Do you still remember what a conjecture is? A conjecture is a statement, opinion, or conclusion based on guesswork. In lesson 8, we use construction and definition as tools to better understand our similar figures. We also discovered that a specific relationship between the sides of similar triangles exist. We also found that although the lengths of the sides of similar triangles differ, the corresponding angles are equal in size. We will now use this information to make our conjecture. Do you think that if two angles of a triangle equal to the two corresponding angles of another triangle, the triangles could be similar? As before, we now need to investigate whether our conjecture is true or not. Here we have two triangles. In triangle ABC, the angles measure 52 degrees, 48 degrees, and 80 degrees. We also know that in triangle DEF, angle D is 52 degrees, angle F is 80 degrees. Let's measure the sides of triangle DEF as well as angle E. Using our ruler, we can measure the length of the sides. So side DE equals 12,8 centimeters. FE measures 12 centimeters. And our last side, DF, measures 10 centimeters. Let's use our protractor and measure angle E. Angle E measures 48 degrees. We see that the length of the sides are 12,8 centimeters, 12 centimeters, and 10 centimeters. We also find that angle B is 48 degrees and angle E is 48 degrees. We can clearly see that the corresponding angles in both these triangles are equal in size. Did you notice a pattern in the length of these sides? Here they are again. So we see that AC divided by DF is 5 divided by 10, which is the same as a half. The same is true of BC divided by EF, which also gives me a half. And AB divided by DE also gives me a half. With this exercise, we have shown that in triangle ABC and DEF, the corresponding angles are equal in size and the lengths are in the ratio 1:2. So we have just proven that these two triangles are definitely similar. We can now formulate this conjecture as a mathematical rule. This is called the angle-angle rule of similarity. If two angles of a triangle are equal to two angles of another triangle, the triangles are similar. This can be abbreviated as the AA rule of similarity. AA stands for angle-angle. Here is another conjecture that I would like you to have a look at. If three sides of one triangle are proportional to three sides of another triangle, the triangles should be similar. I will use construction to try and prove that this conjecture is true. Here I have a triangle ABC. Using a pair of compasses, I will find the midpoint of line AB. Place your compass point at A and draw an arc. Just make sure that our arc is wide enough. Using the same radius, draw another arc from point B. Using a pencil and a ruler, join the points where these arcs intersect. We will mark this point as A prime. This is the midpoint of line segment AB. We use the same procedure to mark C prime, which is the midpoint of line BC. In other words, BC prime is half the length of BC. Also, BA prime is half the length of BA. Now, if we measure line segment A prime C prime, we see that it measures 6,6. And if we measure line segment AC, it measures 13,2. These two sides are proportional in the ratio 6,6 to 13,2, or 1 to 2. What do you think we would find if we measure the angles in both these triangles? Let's have a look. Now we can clearly see that these two triangles share angle B. So in other words, these three angles are equal to these three angles in this triangle. These triangles are similar. With this simple activity, we have just proven that our second conjecture is also true. Now we can formulate our second rule for similarity. If three sides of one triangle are proportional to the three sides of another triangle, these triangles are similar. This is called the side-side-side rule of similarity, or the SSS rule of similarity. I will show you how to apply these rules of similarity a little later in the lesson. But for now, let's go on to our third conjecture. Here we have two triangles, GHI and KPM. We have been given that side GH is in proportion to side KP in the ratio 1 to 2. We are also given that side GI is in proportion to side KM, also in the ratio 1 to 2. Do you see that angle G in triangle GHI is 75 degrees? Angle K in triangle KPM is 75 degrees. Do you see that angle K is included between side KP and side KM? This is also true for GH and GI. Angle G is included between GH and GI. Do you think that this information is enough for us to make the assumption that these two triangles are similar to each other? Let's measure the outstanding sides and angles in both these triangles and see what we find. Using our protractor, let's measure the angles. Start off at angle H. Angle H is 60 degrees. Angle I is 45 degrees. Let's measure angle P. Angle P is 60 degrees. And our last angle at M is 45. Now, using a ruler, let's measure the missing lengths. HI is 11 centimeters. PM is 22 centimeters. So we see that all sides of this triangle and this triangle are in proportion. They are proportional in the ratio 1 to 2, and the angles are all equal to each other. Once again, we can formulate a rule for this discovery. It is called the side-angle-side rule of similarity. If two sides of a triangle are proportional to the corresponding two sides of another triangle and the included angles are equal, the triangles are similar. This can be abbreviated as the side-angle-side rule of similarity. In other words, the SAS rule of similarity. Now that we've discovered all the rules of similarity, let's apply our knowledge. Here's a problem that I want you to think through with me. A person that is 1.6 meters tall casts a shadow of 1.8 meters. At the same time of day, a lamppost casts a shadow of 5.5 meters. What is the height of the lamppost? Here is an important fact that will help you solve this problem. Light rays from the sun create shadows that hit the ground at equal angles. We also assume that both the lamppost and the person are perpendicular to the ground. Do you think that any of the rules that we have learned on similarity can help us solve this problem? Let's recap them. We discovered the AA rule of similarity. If two angles of a triangle are equal to two angles of another triangle, the triangles are similar. The SSS rule of similarity. If three sides of one triangle are proportional to the three sides of another triangle, the triangles are similar. The SAS rule of similarity. If two sides of a triangle are proportional to the corresponding two sides of another triangle and the included angles are equal, the triangles are similar. I think that the AA rule of similarity can help us solve this problem. Let's go back to our graphic. We said that the light rays of the sun form shadows at equal angles, so we know that these two angles are equal. We also know that both the man and the lamppost are perpendicular to the ground, so we know that these two angles are 90 degrees. Now, if we apply the AA rule of similarity, we can say that because these two angles are equal to these two angles, these two triangles are similar. We also know that the sides in similar triangles are proportional to each other in a specific ratio. So we can write down all the information that we are given about the lengths of these sides in an equation. We know that the man is 1,6 meters tall and his shadow is 1,8 meters long. And we know that the lampost's shadow is 5,5 meters long. Remember, the unknown value is the length of the lamppost. Because we know the sides are proportional, we can write it like this. 1,6 divided by 1,8 is equal to x divided by 5,5. This is called a similarity proportion equation. Now, if we multiply both sides of the equation by 5,5, it looks like this. 1,6 multiplied by 5,5 divided by 1,8 is equal to x. So the length of the lamppost is 4,8 meters. This type of problem is called an indirect measurement problem. In other words, because we couldn't measure the height of the lamppost directly, we had to find an alternative way to calculate the height. I trust that you've enjoyed this lesson where we applied similarity in triangles. Join me for lesson 10, where we will recap what we learned in our series.